The cloud sounds weightless, but inside a data center, every digital action becomes electricity, heat, cooling, and risk management. Welcome to This Explainer. Today we're going to pull back the curtain and explore the incredible, completely invisible physical systems that actually make our modern digital lives possible. It's a hidden world, and it's absolutely fascinating.
Section 1. The real cloud. You know, when you stream a movie, fire off a quick message, or generate an image using AI, it honestly feels like magic, right? Like it's all just happening up in some invisible sky. But actually, scratch that. The reality is entirely physical. Every single app you use, every prompt you type, every show you binge, it all relies on physical infrastructure. The cloud isn't floating in the sky, it's locked down in heavily fortified buildings right here on Earth.
To really grasp the sheer scale of this physical world, just consider this one number. Right now, there are over 11,000 data centers worldwide, scattered across 174 countries. Think about that for a second. They act as the literal physical foundation of modern society. Without this massive interconnected network of buildings, everything we rely on, e-commerce, banking, global logistics, even just talking to your friends, would instantly grind to a complete halt.
Section 2. The hidden infrastructure. Okay, let's dive into this. Think of a data center not as a big office filled with laptops, but as a factory for computation. A modern data center operates way more like a heavy industrial facility than a typical IT building.
Inside this factory, you've got three core infrastructure systems that have to work together perfectly 24/7. First, the electrical power systems, bringing in mind-boggling amounts of energy. Second, the cooling systems, constantly sweeping away the byproducts. And third, the actual IT infrastructure, the servers, the massive storage drives, the networking switches, doing the heavy digital lifting. All three of these have to run continuously. If one stops, the servers die. It's really that simple.
So, the absolutely crucial physical reality here is this: computation becomes heat. Servers run constantly, pulling in huge amounts of incoming electricity to process all our data. And, thanks to the basic laws of physics, nearly all of that incoming electrical energy eventually converts into intense, blistering heat that floods the server room.
Section 3. Journey of a request. Let's move on and see how this builds by tracking the journey of a single request. What is actually physically happening inside that building, the exact moment you hit send or search on your phone?
Well, it kicks off a lightning-fast chain reaction. Your request travels at the speed of light through fiber optic networks, enters the facility, and hits a specific server rack. That server immediately computes the answer, which instantly triggers a spike of heat. Then the cooling systems rush in to sweep that heat away before the server literally melts down. Finally, the response shoots right back out to your screen. And the craziest part? This entire physical process happens in a matter of milliseconds.
Section 4. The cooling bottleneck. Because of all that intense heat generation we just talked about, we've hit one of the biggest engineering challenges of our time. Inside these buildings, cooling has absolutely nothing to do with human comfort. It is strictly about equipment survival. If the cooling systems stop, temperatures inside those racks spike in seconds, and the servers will literally shut themselves down or permanently fail just to protect their circuits.
Now, what's really interesting about this comparison is the dramatic shift being caused by artificial intelligence right now. A traditional server rack, the kind we've used for years, draws about 7 kilowatts of power. But a modern hyperscale AI rack, packed to the brim with high-performance chips, can draw 50 kilowatts or more. That is a massive, unprecedented leap in power density. It means an unbelievable amount of heat is suddenly being concentrated into a very, very tiny space. Because of this extreme heat coming off AI chips, traditional air conditioning, just blowing cold air down the server aisles, it just isn't cutting it anymore. The whole industry is practically being forced to transition toward liquid cooling. They're actually bringing fluid, like water or specialized coolants, directly to the microchips. In some cases, they're even fully immersing the entire server in a liquid bath to absorb heat way more efficiently than air ever could. And to manage all that heat once it leaves the server, a lot of modern facilities are using massive units called dry coolers to reject it right into the atmosphere. This enables a really clever trick called free cooling. Basically, when the weather outside is cold enough, the facility can cool the servers using just the ambient outside air. This is a game changer because it conserves an enormous amount of water compared to old-school evaporative cooling towers. And believe me, conserving water is a serious priority for these operators because the raw numbers are just staggering. To put it in perspective, a typical 100-megawatt hyperscale data center in the U.S. can consume roughly 2 million liters of water every single day. That includes water used directly on site for cooling and the indirect water footprint from the immense power generation it requires. 2 million liters.
Section 5. The uptime imperative. Alongside the threat of overheating, there's another existential fear keeping engineers awake at night: power failure. Data centers are actually designed around the absolute certainty that equipment and the utility grids they rely on will eventually fail.
So, to combat inevitable failures, they rely on redundancy. Redundancy simply means duplicating critical components so operations continue even if a system crashes. If the local city grid goes dark, massive uninterruptible power supplies, or UPS systems, instantly kick in with battery power. The servers don't even blink. Then, within seconds, these gigantic backup generators fire up to carry the entire load for as long as the blackout lasts. That guarantees zero downtime, period.
Facility engineers measure this backup capability in tiers. If your baseline requirement is N, an N+1 design means you have exactly the components you need to run plus one single backup component, just in case. But for mission-critical facilities, they often go with a 2N design. That means having completely independent, fully mirrored backup systems, literally a clone of the whole shebang. If one entire power or cooling path dies, the other side takes over flawlessly.
But keeping all these primary systems and the redundant backups running takes an astronomical amount of energy. Global installed data center capacity recently blew past 122 gigawatts. To put that massive number into perspective, it requires the equivalent energy output of dozens of large-scale nuclear power plants operating at full capacity strictly to keep the internet turned on. Section 6. What changes next? Look, the demand for all this compute power is only accelerating. Current projections suggest that by the year 2030, data centers could consume more electricity globally than the entire country of Japan. So how exactly do we sustain this massive infrastructure as demand continues to soar?
And this brilliantly illustrates where the future is heading. The industry is moving toward two major solutions: heat reuse and grid-aware computing. Instead of just dumping all that expensive heat out into the sky, future facilities are actually piping the 80-degree hot liquid coming off their servers directly into local district heating networks to warm nearby homes. Plus, they're developing smarter software that literally shifts non-urgent computing tasks to times of the day when local grid power is cheapest and most plentiful.
We're also seeing some incredibly advanced mechanical designs, like combining those dry coolers we mentioned with something called an adiabatic assist. What this means in plain English is that the data center can carefully balance its critical trade-offs in real time. It can completely minimize water use on cooler days, but when an extreme heat wave hits and the servers are in danger, it strategically sprays a fine mist of water to safely boost its cooling capacity.
Which brings us to a final, profound question. Will our massive, hidden physical infrastructure eventually limit our digital growth? The cloud feels infinite, weightless, and boundless to us, but the land, the power grids, and the water supplies required to sustain it are firmly rooted in physical reality. Adapting these physical systems fast enough to sustain our digital future, that is absolutely the great engineering challenge of our time. Thanks for joining us as we uncovered the real systems behind the screen. I hope you're leaving with a whole new perspective on every single digital click you make.